All right, hi there. This is a continuation of the lesson on graphing sine and cosine functions, where we're looking at transformations of the parent functions of sine and cosine that have changes in amplitude, which would be a vertical stretch or compression or reflection across the x-axis, and also looking at a change in period, which would be a horizontal stretch or compression. So when we're looking at graphing our sine and cosine today in this lesson, we're just looking at this form right here. So we have our A parameter, which controls our vertical shifts or our vertical stretches, compressions, and reflections across the x-axis. And we have our 1 over B parameter, which controls a horizontal stretch or compression in these problems. And what we need to learn about how it applies to trigonometric functions is that our A parameter is actually part of what we call amplitude of a sine or cosine function, and our 1 over B helps us calculate the period, which is the interval over which a single wave is completed. So that's what we're looking at here. So the period of a sine or cosine function, which we use a capital P to represent, is 2 pi, which is the period of the parent functions, both sine and cosine, divided by the absolute value of the 1 over B parameter. You can also look at that, since this would be times the reciprocal of this, as 2 pi times the reciprocal of whatever value you have here in the 1 over B position, times its absolute value. Both will work just fine. And which one you want to use sort of depends on whether your parameter here is a fraction or a whole number. Then you have your amplitude, and your amplitude we are looking at being half the distance between the relative maximum or relative minimum values of the function. And it is the absolute value of our A parameter. Then we have our midline. Midline, remember, is the line that goes through basically the halfway point between the relative maximums and minimums. And it has an equation, so it's horizontal here, of y equals k. Now, in the problems that we are doing today, you'll notice there's no k parameter. So that's because the k's are 0 in this structure. So we're looking at problems today, graphs of sine and cosine, where we're looking at y equals 0 as our midline because our k value is going to be 0. Later on, we'll look at when k is something else. So we want to determine the period. We want to determine the period, the amplitude, and the midline before we start graphing. And then we'll transform those key points we talked about with the parent functions. So the zeros are x-intercepts, the relative maximum and the relative minimum in the first cycle. And then we will go ahead and transform them using the stretches, compressions that exist. And one thing that I want to point out that is often helpful with these problems is that to figure out your scale for your x-axis or your theta axis, a strategy that can be used is dividing the period that you calculate by 4. And then after you graph the first cycle, you'll extend to the rest of the interval that you're graphing over, and you'll be able to just draw your smooth curve, which is your wave. All right, let's look at this problem. So here we're looking at g of x equals 1/2 times sine of 4x, and we're going to graph it over the interval from 0 to 3 pi, where we include those end values because of the brackets. First thing, though, we want to do is find the period, amplitude, and the midline. So our period here, remember, this is our 1 over b parameter. And so our period is equal to the parent function's period, which is 2 pi, divided by the absolute value of 1 over b, which is 4. And so in this case, I would just use this form, and that reduces to pi over 2. So pi over 2 radians is the interval over which we get a 1 complete wave for the sine function. The amplitude is the absolute value of a, and our a parameter is this 1/2. So that would be a half a unit. So basically from our midline, the relative maximum is a half a unit above that, and the relative minimum is a half a unit below that. And our midline, y equals k, is y equals 0, because our k value here, there's no plus or minus after the 4x, And so that is our k value right there. So that's our x-axis, by the way, in case you've forgotten about that. That's the equation of the x-axis. So the x-axis is the midline of this function. All right, so when we go to graph it, one of the things I want to figure out is what scale do I want to use on my x-axis? The y-axis is pretty easy to figure out because it's all based on what you want to do with your amplitude and getting that in there. So for my scale, a strategy I can use is to take the period I calculated, which is pi over 2, and divide it by 4. And remember, this would be mathematically pi over 2 times the reciprocal of 4, so 1/4. So that would give me pi 8. So a nice easy scale to use here would be that every unit would be represented by pi 8 radians. The problem with that is that we would need 8 squares for each pi interval, and we have 3 pi, which means we would need 24 squares. So we have 2, 4, 6, 8, 10, 12, 14, 6. Like we have 18 squares at all. So unfortunately, this will not work. So what I'll use then is a little alteration of this. So I will just make this a little bit bigger. So I'll double this, take my pi 8s times 2, and instead of using pi 8s, I'll use pi 4s. So that means I need 4 squares for each pi. And so that would be, for 3 pi, I'd need 12 squares. So I have plenty of squares for that. So this is going to be my scale factor for x. All right, so in graphing, draw my axes. And from 0 to 3 pi, so I'm going to push my y-axis over here. And I think that I will use a y-axis scale of a half unit. I don't know if I can get this to line up or not. I guess we'll just go with that. So I'll make this a half unit. I'll make this 1, and this will be -1. And then this would be pi 4ths. And then pi halves, and then this would be 3 pi 4ths, and this would be pi. This would be 5 pi 4ths. This would be 6 pi 4ths. This is 3 pi halves. 7 pi 4ths, 8 pi 4ths. There's my 2 pi. This would be 2 1/4. This would be 9 pi 4ths. This would be 10 pi 4ths, which would be 2 1/2 pi, so 5 pi halves. And then this would be the next one, and this would be my 3 pi. So basically you can see how every 2 units is 1/2 pi. That's 1/2 pi, 1 pi, 1 1/2 pi, 2 pi, 2 1/2 pi, 3 pi. So this is the interval over which we are graphing this sine function. Now, until you get comfortable with the parent function itself, what you want to do perhaps is graph the key points for the sine function, the parent function, sine of x. So what we know is that at 0 degrees, our sine value is 0. And then at pi over 2, sine is 1. At pi, sine is 0. At 3 pi over 2, sine is -1. And at 2 pi, sine is back to 0. And these points are the ones we're going to transform using this. So what this is saying is that since in this interval right here, this is what we're looking at. So our factor of 4, what this is representing, this is actually a horizontal compression by a factor of 4. And so it's going to squish all of these 1/4 of the way. And so we're going to look at that. And then this right here, the amplitude of a half, that's our A factor. So this is a vertical compression by a factor of a half. All right, so what's going to happen? Remember, 0, 0 is not affected by any stretches or compressions, or reflections. So it is going to stay exactly there. So we're going to have this point. And then what's going to happen with pi over 2 is that it's going to be horizontally compressed by a factor of 1/4. So we're going to divide by 4. So we've got our factor of 1/4 there. And so this distance, the horizontal distance here, compresses by 4. So it's like dividing this space into 4 equal pieces. So this point is going to end up right there when it's compressed. And then it has a vertical compression. This vertical distance of 1 unit compresses by half, so it ends up down here. Pi is going to compress by a factor of 4. So it's going to be 1/4 the horizontal distance. So it's now at 1/4. And then it's going to stay there because if it's on the x-axis, it's not affected by vertical compressions. So your zeros are not affected by vertical compressions. And then 3 pi over 2. This distance of 6 units is compressed by 4. So 6 divided by 4 is 1.5. So basically we're looking at it being 1.5 away and then compressing by a factor of a half vertically. So this vertical distance compresses by a half. And then 2 pi, this distance of 8 squares, compresses by 4. So 8 divided by 4 is 2. So it's now 2 away. And that's where it goes right there. So this is the first wave of our function. And so now what we're going to do is extend that. So what happens is that you'll notice at the halfway marks, we have our maximums and minimums. So we have maximum, and then a 0, and then a minimum, and a 0, and then a maximum, and then a 0, and a minimum, and a 0. And it just keeps going like that. And we want to keep doing this pattern until we get to the end of our interval at 3 pi. All right, and then we complete our wave. And that is our g of x. All right, I thought I could get both of these examples into one video, but the explanation does take a while. So you're going to have to switch over to part 3 now to get the example, to take a look at the example of how we're going to graph a cosine function. See you there.